precious students. I hope you are all doing well. You are welcome back to our integrated science class. We're going to continue with what we are doing under electricity. In our previous section, we continue to look at some calculations, and we ended the section by looking at questions that are in word problems. Our first set of questions we looked earlier under calculations involve diagrams, and from the diagram you are asked to do some calculations. But we went further by looking at questions where diagrams are not given, but they are given in word problems, and then you are rather asked to draw the circuit diagram and then do some calculations. We're going to look at one more question with respect to that aspect of calculations, and then we'll continue to look at today's work, that is electric power and energy. So we ended the last section on question 4. We're going to look at another question, that's question 5. Okay, so question 5 reads the two power resistors of resistances 3 ohms and 5 ohms are connected in series with resistors of resistances 4 ohms and 6 ohms and a battery of 5.0 volts. Question A says draw a circuit diagram to show the arrangement. Question B is calculate the I effective resistance in the circuit, I effective current in the circuit, I current passing through each of the power resistors, and then the last question IV voltage across the 4 ohm resistor. Voltage across the 4 ohm resistor. Okay, so let's look at the solution. Your solution, question A, is asking for the circuit diagram. So here we have first portion of the question says that there are two power resistors. So you show in the diagram, you show the arrangement of the power resistors. So we have the power resistors, 3 ohms, and then we also have 5 ohms. So that's for the two power resistors, and then they are connected in series with two other resistors, 4 ohms and then 6 ohms. So you have the 4 ohm resistor, and then have the 6 ohm resistor. It doesn't matter, you can decide to even bring one of this here. So your 4 ohm can be here and the 6 can be here, or even both can be on the same side. It doesn't matter. And then you have the battery. I thought a battery consists of just 2 or more cells. So I've drawn battery consisting of 2 cells. And the battery was of 5.0 volts. Okay, so this is your diagram. As you have your current flowing in this direction. Okay, so this current flows, it gets here, and then it will divide into 2. This, that. Some of the current will pass through the 3 ohm, some will also pass through the 5 ohm. And they recombine, the 2 current combine, and then it flows through the 4 ohm, the 6 ohm. And then it comes back again to the junction. Okay. So let's say that from here let R1 equals 3 ohms, R2 equals 5 ohms, R3 equals 4 ohms, and then R4 is equal to 6 ohms. Yeah. So let's also say, let's say the current split here reach here, because this is R1, this is R2. So the current here will be I1, and the one flowing through this one will be I2. So when the total current gets to this one, it's split into I1, I2. I1 passes through the R1, I2 passes through R2. The I1 comes here, the I2 comes, they combine. And as they combine, they form the total current. And the total current will pass through R3 and then pass through R4. R4. Let's say that the voltage across this is Vp. So the voltage across the power resistors is Vp. And then as part of the question, the last question, you're supposed to determine the voltage across the 4 ohm resistor. So the 4 ohm resistor, we labeled it as the R3. So let's say the voltage across this one is V3. Nothing was said about you finding the voltage. If you are supposed to find them, you would have labeled as V4 because the 6 ohm is the R4. Okay, so the question B says calculate the effective resistance in the circuit. We've come across a question involving a diagram where we have resistors that are in power and then the power resistors connected in series with other resistors. So from here, these two are in power. I told you if you have a diagram of this sort, you first of all have to find the total resistance for the power resistors. And then whatever you get, you add it to the other resistors that are connected in series. So that's the first thing you're going to do. You're going to look for the total of the total resistance of the power resistors, that is R1 and then R2. So V. So total resistance of the power resistors R1 and R2. We are labeling that as RP. So because R1 and R2 are in parallel, we use the relation 1 over RP will be equal to 1 over R1 plus 1 over R2. So 1 over RP will be equal to 1 over R1 is 3 and then R2 is 5. And then have 1 over Rp to be equal to 8 over 15. 8 over 15. Okay, so 1 over Rp is equal to 8 on 15. So if you make Rp the subject, your Rp will be equal to 15 over 8. And 15 over 8 will give you 1.875 ohms. Okay, so that is for the total. There is the total of the power resistors. And the total of the power resistors is in series with the R3 and R4. And we said that if resistors are in series, the total is determined by adding the resistances. So the total of this is Rp. The Rp is in series with R3 and R4. So the overall or the effective resistance in the circuit will be the Rp plus R3 plus R4. So effective so the I, that's Bi, effective resistance in circuit, that's RT. Your RT here will be the sum. So Rp plus R3 plus R4. So the total of this, which is Rp plus this plus this. Rp had 1.875 plus R3, which is 4, and then R4, which is 6. You add this, that will give you 11.875 ohms. Okay, so that is the effective resistance in the circuit. Okay, so please, I said if you have a diagram consisting of a power resistors which is in turn connected in series with other resistors, you first of all look for the total of the power resistors. After getting the total, then add it to the other resistors that are in series. So that's what we did. So we look for the total of this power resistor. We are saying the total of this is Rp. We label that as Rp. So because these two are in power, we determine the total resistance as 1 over Rp plus a 1 over Rp to be equal to 1 over R1 plus 1 over R2. You do your substitution, you get 1 over Rp equals 8 on 15. You are making Rp. Your Rp becomes 15 on 8, which is 1.875. I'm saying that the total of the power resistor, which is Rp, is in series with R3 and R4. So the effective resistance in the circuit will be the Rp plus R3 plus R4. So that's what we did, and the answer given us 11.875. So that is for Bi. We're going to continue to look at the BII. We are looking for the effective current in the circuit. From the diagram, the effective voltage is the 5.0 volt. So you have effective voltage. Effective voltage DC is equal to 5.0 volt. Effective current, that is IT. said that we always, if you're looking for the effective current, you always need of the Ohm's law, V equals IR, and then make I the subject, with is V on R. So our effective current will therefore be equal to the total voltage over the total resistance. So our total effective current is the effective voltage over the effective resistance. The effective voltage is 5, and the effective resistance is 11.875. That's the answer we had in the BI. And when you do that, that'll give you 0.421 amperes. That is true. 3 decimal places. Okay, so the effective current here is 0.421. 0.421 amperes. 0.421 amperes. EII, it says you should look for the current passing through each of the parallel resistors. So you want the current flowing through the R1, which is labeled as I1, and the current flowing through R2, which is also labeled as I2. I told you that anytime you have a diagram consisting of both parallel resistors and then series resistors, you've got to look for the voltage across the parallel connection. So the voltage across the parallel connection is what we've labeled as here as VP. So you look for the VP, and that voltage is the voltage across the R1 is still equal to the voltage across the R2. So once you get VP, your VP will help you to determine the value of I1 and I2. For you to find I1, it will just be the VP divided by R1. Your I2 will also be equal to the VP divided by R2. So we're going to look for the VP first. We say voltage is current times resistance. The current that is coming here is the IT, and the total resistance here is RP. So if you are looking at the voltage across this power connection, it will be the IT times the RP. So let's look at the voltage across the power resistors. So voltage across the power resistors, R1 and R2. That's what you have labeled as VP. Your VP here will be equal to the current that is coming into the power connection. That's the total current times the total resistance of the power resistor, which is RP. So it will be IT times RP. Our IT we have 0.421. The RP we had the power resistors we had 1.875. So when you multiply that, that will give you 0.789 volts. That is with 3 decimal places. Okay, so we now have the voltage across the parallel connection. So we now look at the current flowing through each of the parallel resistors. So current passing through 3 ohm resistor That is what you labeled as I1. You don't know. But as I said, your I1 will be the voltage across the power connection, which is VP, over the R1. So that is VP over R1. Our VP is 0.789 over R1, which is 3. So that gives you 0.263 amperes. So 0.263 amperes. Let's look at the current flowing through the 5 ohm resistor. So current passing through 5 ohm resistor. That is what's labeled as I2. So here your I2 will also be equal to the VP over the R2. So VP over R2. Our VP is 0.789 over R2, which is 5. And now give 0.158 amperes. So this is I1, I2. As I said, it is your IT we get here, and device you get I1, I2. It means that if you add these two, your I1 plus I2 should be equal to IT. So if you add this, the 0.263 to the 0.158, that should give you the total current, which we calculated to be 0.421. 0.421. So the total current was 0.421. So that is for B, I. The last question here is the IV. Question B, IV. Since you calculate the voltage across the 4 ohm resistor, so voltage across. Okay, before we look at the voltage, I said that the total current flows through here. It divides into I1, I2. I1 comes in, I2 also, so they combine to form the total current. And then the total current flows through the R3 and R4. So the current flowing through the 4 ohm resistor, that's R3, is equal to the IT. So current passing through 4 ohm resistor the 4 ohm resistor is I3, so I'm making is R3, so I'm labeling that current as I3. It's equal to IT. So your I3 will be equal to 0.421 amperes. So you can now look at the voltage across. So voltage across 4 ohm resistor. That's V3. That's what you're looking for. So your voltage is the current times the resistance. So our V3 would therefore be equal to I3 times the resistance R3. So our I3 is the same as the IT, which is 0.421, and then the resistance R3 is 4. So that's 1.684 volts. Okay, so that is the voltage across the 4 ohm resistor. Similarly, if you're supposed to find the voltage across the 6 ohm resistor, the current flowing through the 6 ohm resistor will also be equal to IT. So if you want the voltage across the 6 ohm resistor, it will be the total current, that is 0.421 times 6. And then when you multiply, that gives you the answer. That's the voltage across the 6 ohm resistor. Okay, so this completes question 5. So we're going to end the calculations on this aspect of questions. I'll be giving you more of the calculations as tutorial questions, which will be loaded onto the Google Classroom platform. We're going to continue today's class by looking at electric power and energy. So we're going to look at electric power and energy. Okay, so first of all, we're going to look at the definition of these two terms. So electric power. Now, what is electric power? What is electric power? In previous class, before electricity, we've looked at force, work, power, and energy. So we've come across the word power before. We said power is the rate at which work is done with respect to time. So we defined power as the rate at which work is done with respect to time. So if you're talking of electric power, say that it is the rate at which a unit electric charge is transferred between 2 points in a circuit per unit time. Okay, so the rate of transferring a unit electric charge between 2 points in a circuit per unit time. So that is electric power. The work done. So it is the work done in transferring a unit electric charge between 2 points in a circuit per unit time. So that is electric power. The work done in transferring a unit electric charge between 2 points in a circuit per unit time. So here electric power is also equal to work done over time. Right, so but before we look at the relation or the equation for electric power. We've come across work done. Under electricity, your work done. So let me write this as note. Work done. The electricity W is calculated as charge, the electric charge represented as Q. You come across that. That charge is represented as Q times voltage, which you know is represented by V. So it implies that your W is equal to QV, charge times voltage. If you are to make the charge the subject, your charge will be the work done over the voltage. Your voltage will also be equal to the work done over the charge. Okay, so from definition, we are saying that electric power P is work done also. We know that when we started looking at current and electricity, I told you our current is equal to the electric charge over time. So if you make the charge the subject, your charge becomes the current times time. So it implies that it says that Q is equal to IT. If you do your substitution, it means that the work done, in place of Q, you put IT. So that will be IT times V. If you rearrange that, your work done will also be equal to IVT. Okay, so your work done is the charge times voltage. And in terms of current and time, your work done is also equal to your current times voltage times the time. Okay, so now let's look at the equation for electric power. So from definition, we said that electric power is the work done, that is W, over time. So from this equation, your work done, as I said, is IVT, and at the time is T. So you look at this, the T cancel out. So it implies that your P, your electric power, is equal to the current times the voltage. Okay, so that's the relationship between electric power, current, and voltage. So the power is equal to the current times the voltage. Power equals to current times voltage. Okay, we also know that from Ohm's law, V equals IR. From Ohm's law, the voltage is equal to the current times the resistance. So in place of the voltage, you can put current times resistance. So it implies that your electric power will also be equal to the current times the voltage, that is current times resistance, and that becomes I squared R. Okay. So your power is also equal to the current squared times resistance. So this is the relation for power in terms of current and voltage, and then this is the relation for power in terms of current and resistance. Also from the Ohm's law, you can rather make I the subject. So if you make I the subject, from V is equal to IR. If you make I the subject, your I is equal to your V on R. And then you can substitute this into P equals IV. So in place of I, we put V on R. When you do that, your power becomes the current, which we are saying is V over R, times the V. And that gives V squared over R. Okay, so this is another relation for power, but this is in terms of voltage and resistance. So we will look at three different relationships for power. The first one is in terms of current and voltage. The second one is in terms of current and resistance. And this last one is in terms of the voltage and then the resistance. The voltage and the resistance. Okay, so the unit of power is unit of electric power is equal to watts, represented as W. Okay, so that is the unit of power. Yeah, your work done, the work done W is in joules. So that's the unit of work done, joules. And then your time here is in seconds. Okay, we've already come across the unit of current, which is in amperes, voltage in volts, resistance in ohms. Okay. Now, so let's look at electric energy now. Electric energy. So we say electric energy is the energy that is supplied by generating a power of 1000 watts in 1 hour. So when a power of 1000 watts is generated in an hour, the energy that is supplied is what we refer to as electric energy. So we say it is the energy supplied when an electric power of 1000 watts is generated in 1 hour. Or you can see is the energy supplied in generating an electric power of 1000 watts in 1 hour. Okay, so the energy supply when an electric power of 1000 watts is generated in 1 hour. That's what we refer to as electric energy. So from definition, electric energy you represent this as E is equal to the power, electric power, times time. So you have E is equal to PT, power times time. So your unit of electric energy is equal to kilowatts R, which is represented as small k WH. So the K there is a kilo, and then the W is the watt, and then the hour is the H. So that's the unit of kilowatt hour. What it means that where your P power is in, where power P is in kilowatts, kW, and then the time T is in hours each. Okay, so calculating electric energy, your power is in kilowatts, and then the time is in hours. The time is in hours. Note of this: 1 kilowatt hour. When I say kilowatt hour, 1 kilowatt hour is equivalent or is equal to 1000 watts. So the kilo there actually means 1000. So 1 times 1000 give you 1000. So it means that if you are converting kilowatt hour to watts, you multiply by 1000. So if I have 2 kilowatts, I'm converting it to watts, I'll just multiply the 2 by 1000, and that'll give me 2000 watts. And if you're converting watt to kilowatts, then in that case we divide by 1000. We divide by 1000. Cost of electricity. Cost of electricity. What we call the light bill. Light bill. So cost of electricity. So it's simply the cost of producing electric energy of 1 kilowatt hour. So that is cost of electricity. So it is the cost of producing an electric energy of 1 kilowatt hour. So the cost of producing electric energy of 1 kilowatt hour is what we refer to as cost of electricity, or otherwise you can say is the cost of generating electric power of 1 kilowatt in 1 hour. So the cost of producing electric power of 1 kilowatt in 1 hour, or the cost of producing electric power of 1000 watts in 1 hour. That's what we refer to as cost of electricity. Cost of electricity, I'm representing that as C, is equal to the electric energy times U. I'll define each of this. So where C is equal to cost of electricity, and then your E here is electric energy in kilowatt hour, and then your U is equal to unit cost of electricity. Okay. So for instance, in Ghana, let's say the unit cost of electricity is, if it is 2 cedis, 2 Ghana cedis, you just have to multiply the electric energy that was used in the month, and then you multiply by 2 cities, and that will give you the cost of electricity for the month, or what we call the electric bill for the month. Okay, now, so this is a summary of the equations we've come across. Summary of equations. A summary of the equations we've come across. So 1, we said that work done is equal to the charge times the voltage. 2, your work done is also equal to the current times voltage times time. Then 3, the electric power is work done over time. 4, we said the electric power is also current times voltage. 5, step power is equal to the current squared times the resistance. 6, the electric power is also equal to the voltage squared over the resistance. And then 7, we said that electric energy is equal to power times time. Power times time. And then 8, cost of electricity is equal to the electric energy times the unit cost of electricity. So these are some of the equations we came across. And also don't forget, probably I should have started with this. We said that your charge is equal to the current times the time. Current times time. We came across this earlier on. Okay. So these are equations that will help you in answering calculations and electric power and then energy. We're going to look at related questions or calculations and like this. So related questions. Question 1. So a charge of 96,000 coulomb was transferred across a potential difference of 50 volts in an hour. Calculate the A, work done, and then B, power generated. Okay, so you have this simple question. A charge of 96,000 coulomb was transferred across a potential difference of 50 volts in an hour. And then based on that information, you have to calculate the work done and the power generated. And so let's look at the solution. So from the information, we were given a charge. This is a charge. Charge Q is 96,000 coulomb. So now that's the unit of charge, coulomb. Q. Potential difference here. I told you in calculation, your potential difference is the same as the voltage. But in definitions, there's difference in them. But when it comes to calculation, your potential difference is the same as the voltage. So your PD is the same as the voltage. So voltage V is equal to your 50 volts in an hour. So the time there, an hour. So an hour is 1 hour. 1 hour. 1 hour. We're going to calculate for work done and power. I told you when we're looking at work done, the formula for work done and then power. I told you that the unit of the time there is in seconds. But from the question, the time is given in hours. So you have to convert the time in hours to the time in seconds. We've come across these conversions in some previous topics that we looked at under work, power, energy. So in converting hour to seconds, you multiply by 3,600. Don't forget, I told you that if you're converting hour to minutes, you multiply by 60 because 60 minutes gives 1 hour. So you multiply by 60. And we also know that if you're converting minute to seconds, we multiply by 60 because 60 seconds give 1 minute. So if I now want to convert hour to seconds, then it will be the 60 times 60. And 60 times 60 gives you the 3,600. So that's why we are converting hour to seconds. We multiply by 3,600. 3,600. So this is equal to 3,600 seconds. So that's the time in seconds. And the first question is asking to find the work done. So work done, W, we don't know. Now how do you find W? If you come back to the summary of the equations, these are the equations that contain W. W equals QV, W equals IVT. From here to we have P equals WT, so you can make W the subject. From the information, we have the charge, we have the voltage, so it means that we can use equation 1. We can use equation 1. We can't use equation 2 in this case because why? Even though we have the voltage and the time, we don't have the current, we don't have the I from the information given. So we can't use equation 2 to find the W. Similarly, for us to use or make W the subject, we need the power and the time. We don't have the power, so we can't use equation 3. So the only equation we can use is equation 1. That's the charge times the voltage. Okay, so we have W equals QV. So our work done will be equal to the charge, which is 96000 times the voltage, it is 50. 96,000 times 50 gives you 480. So that's 4,800,000 joules. The unit of work done is in joules. Okay, so that is the work done. And then the B is asking to find the power. From equation 3, it said that power is equal to work done over time. We've calculated for work done. We also have the time given in the question, so we can calculate for the power using equation 3. So the power here using equation is work done over time. The work done is 480,000 over the time 3,600. And that is equal to 1,333.333. That's with 3 decimal place. And the unit of power here is in watts. So that is for question 1. For question 1. Okay, because of time, we're going to end the calculation here. Probably tomorrow we're going to look at more examples. Until we meet again, enjoy the rest of the day. Bye.